All right, welcome back, everybody. Hope you had a good weekend. Class 25 starts right now. It's Monday, March 30th, 2020. I want to get you all started with a few warm-ups. These are circuits that are pretty simple. I hope that you will know exactly what I'm doing, so I'm going to go through them pretty fast. However, I would like to make sure that you know how to do it by yourself. So I'm going to ask that you grab a blank sheet of paper, jot down the following circuits. Before we do any work, I've got 3 of them. I want you to draw somewhere on your sheet. Make sure you've got room to work. I've given myself this amount of space. That is probably sufficient for this one. I want you to notice on this particular one, I've given a value to this unknown R, 60 ohms right here. I hope you will recognize this as the voltage divider. And a typical problem involves wanting to know how much voltage is across this lower one. I haven't really talked about applications of this circuit, but it's very often used in what we call bias circuits. And for those of you interested in electronics, you might want to know how you would amplify a signal, for example. For example, if you have a small signal coming out of an iPod or a computer jack, headphone jack, and you want to boost it, amplify it, you often have to put it through a circuit called an amplifier circuit. And one way of doing that involves taking a circuit component called an op-amp, bringing in your signal that you want to listen to and having it biased at some voltage value where there are resistors above and below. So this spot right here acts like this guy right there, and it helps set a minimum level for things like amplitudes in these bias circuits and these amplification circuits. We don't need to know that, though. We just want to do a simple Ohm's law analysis. All right, so you got a voltage in. We've got 2 resistors in series, and we want to know what's the voltage out. The next one, we've got a battery there on the left. It has what we refer to as an internal resistance. Here's the internal resistance, 0.5 ohm. This is modeled as being a resistor inside of the battery itself, and you can pretend that the battery has a perfectly ideal source of EMF, a seat of EMF, and we'd like to know how much current flows when this is turned on and there's some internal resistance. We're going to start with that switch open and then close it. We're going to need to know a voltage here, so let's make this your typical 1.5 volt battery. So we've got a 1.5 volt battery. That does not change, but as it ages, the internal resistance increases. These are both 6 ohm light bulbs. We're going to start with 1, then we're going to add that second one when we close the switch up here. All right, so you get that circuit drawn. Let's go to the third one. Ooh, Kirchhoff's law. I want to race you through how we set this one up. Then I'm going to pause my recording. I'm going to let you practice how to do this and give yourselves a way of seeing, did I really remember all the steps myself? Then we're going to solve it. Now, you may notice I don't have a lot of room to solve this guy, so I'm going to do that on this sheet here. So there should be exactly the same values. And I wanted you to notice before we get started that this one is also going to have the batteries in places that are a little bit unusual, not the same place that I had them last time. Mr. Dowling, you always had the battery over here. Well, tough luck. I've decided to switch things up on you. I'm also going to use some tricks. I'd like you to notice that in this first portion of the circuit over here on the left, I've got 2 resistors, and they are in the same part where a single current flows. I'm going to combine those resistors. So when I go to my work over here on the next page, when I do it, you're going to see that I combine things that can be combined before I start solving. All right? Let me go back to this so you can see that circuit. I'm going to get rid of that stuff on there so you can see it clearly. And I'm going to pause and ask you to pause the video so that you have everything down. So we have 3 circuits. This is number 3. Here's number 2. Here's number 1. Pausing. All right, circuit number 1. This is the voltage divider. We already worked this out. You did this as part of a homework assignment as well. So I'm not going to redo it. Using a simple Ohm's law analysis, you add together the resistors in series. That would be 160 ohms. You figure out the current. I is equal to V over R total. But we don't know. We don't know what V is, Mr. Dowling. Well, we know it is V in, and so we can use that as a fixed number in this experiment. What we then do with that known current, because it all has to flow through this bottom resistor, is we use the fact that the voltage across that resistor is what is being referred to as V out here. And we just use Ohm's law again, only now we don't use the total resistance, we use just the bottom 100 ohm resistor. And so I want to do it like this first of all, and then remind you that I is this combination of things over here. Our total is the sum. So when I take I and replace it with this expression, what I'm going to get is something that involves the input EMF, V in, like that. And I've got 1 over R total. Now I'm writing it in this funny way so that you can see what happens when I combine it with R up here is something that can be split up into something that involves only a voltage. Here's your V in, and then everything else is only resistances. And the only resistance stuff is always the resistor on the bottom, which in this case is that 100 ohm guy, and the bottom is the sum. So I'm going to be calling it R60 plus R100, which is kind of a funny way of writing it, but wanted to kind of tie it back in with how we had done this previously, I think. And now our final answer is that the output voltage, V out, is equal to the input voltage times a ratio of resistances. So what I've got is the 100 over 160. So in this case, I have 10/16 of my original input voltage. If that had been, say, 10 volts, I would have 10 volts times 10/16. Now, you can reduce the 10/16, and that would be 5/8. 5/8, as we all know, is 0.625. So you get about 62.5% of your input voltage when you do this. That means if you've got something where you've got a 10-volt supply rail, they call it in the electronics world, you can easily get whatever voltage for a reference that you need for some other part of the circuit. All right, did you get that one right? Give yourself a pat on the back. Well done. Let's go now to circuit number 2. Now this one here, the 0.5 is always in there. So when we first do this problem, when the switch is open up top, we have a resistance of 6.5 ohms, and we have an ideal 1.5 volt seat of EMF, to use that old-fashioned term. So we want to get the current flow. When the current flows, I is equal to V over R. That's going to be our 1.5 over the 6.5. So when I do that, I got 1.5 up here, 6.5 down below. Those are both divisible by 5, so I can probably do this one in my head. I got let's call that one 3. I'm divided by 0.5, in case you didn't notice. And on the bottom, I'm going to have 13, and that's good enough. You could turn that into a decimal if you wanted to, but you know what? That's your job. Now we're going to close that switch. So we close the switch, and what happens next is the total resistance changes, right? In fact, we lower the resistance. This is kind of funny. We lower the resistance by adding another resistor in parallel with the second. Now, if I draw this out, here is my 0.5, and then in parallel, here are my 6s. Make sure you agree that that's what I've got. I've rearranged things, and if I put my ideal battery in there, I usually show my battery over here on the left-hand side, and what I want you to notice is that the ones that are in parallel with each other, these guys here, are equal. So this is going to be equal to 3 ohms worth of resistance. Remember, adding in parallel cuts your resistance. So now we've only got 3.5 ohms. It's the same type of problem. How hard can it be? So I is equal to V over R. Well, I is now going to be 1.5 volts. That has not changed, but the resistance has dropped to 3.5. Once again, just reminding ourselves that there's nothing magical about digital values. We can use fractions. Why not? This is equal to 3/7, and 3/7 has some decimal form that you can look up on your calculator or calculate longhand if you want. But I would like you to notice that the current has increased because of the fact that we have a lower resistance. This means that for lower resistance loads, batteries as they age have a larger current, and more of that energy is dissipated inside the battery, heating them up and making things start to go haywire with their chemistry. So it kills the battery in the short term. If you keep doing it, making it drive current through a small resistance load. For large resistance loads, that 0.5 ohms would never show up. No one would care about it, and the battery wouldn't really heat. Now, related questions that I'm not going to do, but just so that you know what you might be expected to find, how much voltage is available across the terminals? You know, the resistance that's inside is just that, it's inside. In the first case, what I would do, I could figure out the voltage drop across it by using IR, and the current of 3/13 of an amp is being dropped or is flowing through a half ohm, and so the voltage drop inside the battery itself is going to be 3/26. That doesn't sound like a lot, but you have to remember that this is approximately, that's about 3/25, which is about 600, so that's 0.06 volts. So that doesn't seem like very much voltage difference from this 1.5. If I did the same thing down here, the voltage drop inside the battery, well, the current is larger now. It's 3/7. The voltage inside the battery is being dropped across a half ohm of resistance. So because I'm using fractions, I'm converting from 0.5 to a half. So the voltage drop inside the battery is 3/14. That's roughly 3/15. That's about 0.2. That's 1/5. 0.2 volts. That's a lot more. That's a much larger fraction of this. So as your resistance inside the battery increases, this effect becomes more pronounced. As the load resistance decreases, this effect becomes more pronounced. One of the things that you might want to do in addition to this is figure out, all right, what is the power dissipation inside the battery? This is not doing anybody any good. It's just heating up the battery. It is lowering its lifetime and costing you money. So in this case, the easy one to do is I squared times R, I think, because 1/2 is a nice fraction for the resistance, and I is 3/7. That's not easy to calculate out in decimal form, but in fraction form, it's no big deal. So we got 3/7 times 3/7 times 1/2. And inside the battery, if we calculate that out, let's see if we can do this in our heads without pulling out our calculator. We've got 3 times 3 is 9. 7 times 7 is 49 times 2. That's basically 100. So that's roughly 9/100 of a watt. So that's about 1/10 of a watt. That doesn't sound like a lot until you're a little battery forced to dissipate that. All right, I'm going to go to the next screen, and I'm going to pause just for a moment. Let you look at it again. All right, I'm back. I only have a minute, so I got to go fast. Here's my starting point. I'm going to mark that as start. The thing I like to do is do my currents at this node up top. So there's my top node. I want to have the currents flowing in equaling the currents flowing out. So there we go. There's I1. There's I2. And here comes I3. It's going to flow down. So at that top node, we're going to use Kirchhoff's current law at the top node. And when we do that, we always get the same thing if we apply this method. At the top, we have I1 equaling, I2 plus I3. Always get that. I'm using the mouse, so this is a real pain, sorry. That's going to kill. It's going to cut out on me in a moment. So let's quickly do from the start loop number 1, like that. Call that L1. And then in a different color, we're going to do loop number 2 from that start all the way around like that. And we're going to call that L2. Now, we can add together the resistors on the first leg. 0.3 plus 1.5 is 1.8. Add together the resistors on the outside leg, the 6 and the 0.3. And I'm going to give you in a moment the answers. Here's your answers. Go. There they are. Hope you enjoyed that.